Hello students, I wanted to do a couple word problems in this video. We've been working on differential equations, and the classic word problem is something to do with Newton's law of cooling. And so just reading it carefully, the rate, so that's our keyword rate that we're doing a differential equation, at which an object's temperature is changing at a given time little t is proportional to the difference between the temperature big T and the temperature of the surrounding environment T naught. So let's just try to set that up without any numbers. We're saying that the rate of change of the temperature, so big T related to time, is proportional. So we usually use K because constant starts with K, of course, to the difference between its temperature, capital T, and the temperature of the surrounding environment, T naught. So that sentence right there can be translated into that differential equation. Now let's solve it without using any of the numbers. One thing that when I was a student was hard is I wanted to plug the numbers in initially, but if you plug the numbers in initially, you have a constant and it's not going to integrate the correct way. So let's try to separate our variables here. And I know I can separate it because I'm multiplying by a function of capital T. So I'm going to divide both sides by t minus t naught and multiply both sides by dt. Integrate both sides, and the left side becomes the natural log of the absolute value of capital T minus T naught. The right side becomes just your good friend KT plus C. So there's our other constant. Now, this natural log absolute value bars, just think about the context of the problem here. We know that we have, if you keep reading, that it's an object that's cooling. And if it's cooling down, that means that it's hotter than its surrounding environment. So its T is higher than the T naught. And so those absolute value bars are redundant because T minus T naught will be positive. So let's exponentiate both sides, canceling out the natural logarithm. Like I just said, we can get rid of the absolute value bars. And like we've talked about in the past, we can drop the c in front here, like that, c e to the kt. And then to solve for the temperature, I'll bring it up to the left side of the screen here. We just have the temperature at any time is equal to ce to the kt plus the temperature of the surrounding environment. And that should match with what you think happens in the real world, that there is some curve where you are cooling, 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 and then there's an asymptote because it is not going to cool down more than the room that it is in, or not necessarily room, but then the environment that it is in. Now that we have our solution, let's use the information given. An object that is kept in a laboratory that is kept at a excuse me, if an object in a laboratory that is kept at a constant temperature cools from 100 to 80 in 10 minutes. And so that really gives me two different pieces of information. It tells me that when t equals 0, we are at 100 degrees, and when t equals 10, we are at 80 degrees. So let's start with the 0 and the 100. The temperature was 100. Actually, I'm going to switch colors here because now I'm kind of doing the next part of the problem. So I'm going to switch colors to blue because we're cooling down. So if we have 100 degrees initially, we can use 0 as our time value. So that's k times 0. And what that leads me to have is 100 equals c plus t naught. And the key reason there is k times 0 is 0 and e to the 0 is 1. So I'm going to hold on to that little equation. I can't do too much more with it, but it will be useful soon. Then it cools to 80 degrees in 10 minutes. So let's use a slightly different color here. So 80 degrees is equal to C e to the k times 10 plus T naught. If we subtract those two values, then we will cancel out the T naught. And so that would give us, subtracting would give us 20 equals C minus CE to the 10k. So that's getting slightly better, I suppose. We'll keep that one for later. One other thing I might want to do right now is just factor out a c. So 1 minus e to the 10k. Okay, I still can't really solve too much more from that. So let's use the next piece of information. It cools from 80 degrees down to 65 degrees after a further 10 minutes. So let's go use black for that initial condition. So we know that if you have 65 degrees, now it's a further 10 minutes, so that's 20 minutes total. So CE to the K times 20 plus T naught. Let's use, it doesn't really matter which one we use, let's use the original 100 equals C plus T naught and subtract those values. Very similar. So we had 35 degrees of cooling, and we can factor out a C and 1 minus e to the 20k. All right, now we're really getting somewhere. With those last two equations, they look very similar. And what I'm thinking is you can either solve for c and equate them, or you can divide those two equations and the c's will cancel out. Either way is equally good. So I'm going to erase this red business over here to give me some space. Let's do the, move that over there. Let's do the setting them both equal to c. So in order to set them equal to c, you're going to divide by the piece in the parentheses, the 1 minus e to the something k. And so what I'll have is two different expressions that are equal. Let's just use black for this. So I have 35 divided by 1 minus e to the 20k. That's from the black equation. And then from the purple equation, I have 20 divided by 1 minus e to the 10k. And then now I've got it down finally to just one unknown, the k value. So let's cross multiply and see what we get. So we have 35 minus 35e to the 10k equals 20 minus 20e to the 20k. Okay, now let's get our numbers on the left side. So 15 equals, and then over here we'll do 35e to the 10k. I'm adding that and leaving the 20e to the 20k alone. Okay, let's divide everything by 5 and factor out an e to the 10k. So if I divide by 5, I get 3 equals, I'm going to factor out e to the 10k. So what's left over? 35 divided by 5 is 7. What's left over? 20 divided by 5 is 4. E divided by e to the 20k divided by e to the 10k leaves me with e to the 10k. Sorry, I squeezed it in there. And then what we want to do is solve for the k value. And how do I get the k value here? Let's see, what am I missing? I'm going to pause for a second. All right, I think that I may want to back up a step here and rewrite this as a quadratic. That's, I think, what I want to do. So let's get rid of that. If we rewrite it as a quadratic, let's have it be 20e to the 20k minus 35e to the 10k plus 15 equals 0. Let's divide everything by 5. So 4e to the 20k minus 7e to the 10k plus 3 equals 0. And you can factor that just by thinking about the terms that are going to multiply and add there. So just factor that to be 2e to the 10k times 2, come on, 2e to the, let me erase that. Let's fix this. Okay, here we go. 2e to the 10k. So those two things will multiply to make 4e to the 20k. And then if we go minus 3, that'll give us 6, and minus 1, that'll give us 7, and that works. There we go. So we end up with two potential solutions here. One solution being from the first factor, and the other one being from the second factor. So we end up with, from this one, if you solve for k, you get k equals the natural log of 3 divided by 2 divided by 10. So I'm going to put a 1/10 here. And similarly with the other one, the only difference is the 3 becomes a 1. And so our other potential k value is k equals 1/10 times the natural log of 1/2. So then you can use this k value to go back and get the c value. And once you have your c value, you can go back and get the t value. So I'm going to erase this work that's in black over here. So I just needed to get my k value, and then we should be able to go from there. One other nice piece of information is that we know that we want the k value to be negative because the object is cooling down. And if you look back at our exponential model, only a negative k value would make it work. And so we know that this one right here is the value that we want because the natural log of a fraction will be negative. Okay, so using that, we know that we can substitute it in to any of these equations that has a k. We'll substitute it in right there. And so that leads me to have 35 equals c times 1 minus, and if I go e to the 20 times a 10th, I get 2 ln of a half. And so that becomes 1/4 because the e and the ln cancel out. So you have a half squared. A half squared is 1/4. And so 35 equals c times 3/4. So c would be 35 times 4/3. 46 and 2/3. Then last piece, we know that c plus t from the blue equation, c plus t naught has to be 100. So if I just subtract that from 100, I get that t naught is equal to 53 1/3. So then I believe we have all the information we need. The temperature of the laboratory is 53 1/3. The C value is there, the K value is there. And so in order to then answer the last question, what is the temperature of the object after another 10 minutes has elapsed? You say the temperature is the C value, 46.6, e to the kt, so we go to the 1/2 natural 1/10 natural log of 1/2. Now we're talking 30 minutes plus the temperature of the surrounding environment, 53 1/3. Okay, and if you go through all of that, you will have 46.6 repeating times 1/8 plus 53.3 repeating. Almost there. Hang with me for another minute here as we crunch those last couple numbers. So we have 46.6 repeating times an eighth plus 53.3 repeating, and we get that the temperature should be approximately 59 and 1/6 degrees. So there you go. Took me a little longer than I thought, but that's walking through Newton's law of cooling and how you can go through a differential equation to create a model. Ask for help if you need anything. I'll make more videos explaining it.